Okay, so the data tilling service, one of the two main services of Brown Dog. This is the outline. I want to start by kind of touching upon the name data tilling service, why that name, and what we're trying to do. Then I'm going to talk about somewhat extensively about two building blocks for the DTS, Medici and Versus. I'm going to give some past use cases where we have applied some of these tools. So I'll talk about the census that came up earlier on today, large-scale video analytics project, some GIS work that we did. And then I'll go into some more technical things. So I left it for the end. So the more technical thing is stuff is at the end. So if you're looking for that, that's going to come later. OK, so data tilling service. So why tilling? You know, everybody kind of knows what till means, prepare and cultivate land for crops. And if you just replace data for land for analysis, right, you start getting a sense to prepare or cultivate data for analysis. And here, right, it's preparing data for analysis. It's not necessarily doing full analysis on it. So if you think about the verb tillage, right, and you replace, you know, you get is the computational preparation of data by algorithm agitation of various types, such as digging, steering, and overturning. Again, agitation, right? And the difference I'm trying to make is that many times with data analysis, there's a lot of prior knowledge that goes into it. And here is a little bit before that step, right? That's where kind of the data tilling happens, right? You prepare the field, right, for later on, for more work. So it's kind of a, you know, mix between this, and maybe you get this, right? You get the matrix, right? But this sounds silly at first until you start thinking about the fact that what we're doing is we're taking the raw data and we're trying to extract this metadata, right? So in a way, you know, what we're trying to do is shake the data and then metadata falls out. And the two together are very important because one gives context to the other, right? So that's what we're trying to do. And it's also, yeah, the context, the view into the raw data. That's what the metadata is. So like I said, pre-data analysis. So not necessarily data cleaning. You know, when you think about your usual kind of pipeline for data analysis, that's the kind of the first step. Not necessarily data cleaning, more like metadata extraction, not full analysis, not perfect results, right? Sometimes you don't know what's going to come out, right? You don't know what's going to be extracted. And apply as many methods as possible. So the idea here is that we throw files at it, and then in the background stuff happens, right? And you know, some of it might be very useful, some of it less useful, but in the meantime, this is going on. And then you worry about how does the user find relevant metadata, right? Because now you have the problem of having a lot of information about that, you know, data itself. So in a way, right, we start with an original file, raw data, and then we start adding all these metadata fields to it, and then try to make sense of the graph, the big graph. So today, you know, earlier on we showed the demo, and I tried to explain what the setup was. But basically, you know, in your web browser, we have this piece of JavaScript that runs, and then it sends it to this cloud of extractors right on the server side. And these are the things that I'll describe in a little bit. And then, you know, on the server side, we cache some information about the data, information about the metadata extracted. And so the web browser and the JavaScript in the web browser is just kind of talking back and forth with the DTS, waiting for, you know, new information to become available, then using that information in the browser to allow you to search the web page for more information that is natively inside that web page, right? So this is what the things are, and this is what that cloud is, and it's a very simple kind of representation of it. But the idea is that you have these front ends, and it says Medici there, but really that's the DTS service. And then things come in, and they get on this extraction bus. And every piece here that you see, it can be deployed on different machines, different VMs, right? So it's all distributed so that we can scale out, right, inside the data center. And you can do this across data centers if you want and all of that. But basically, that file comes in, the extraction bus notifies whoever is listening, and then all these pieces, which are our extractors down below, pick up the message, say, OK, I know how to work on this particular file, right? I know how to handle images. And so they say, okay, let me try something on images, right? And they do that independently of each other. They do that independently of the front end. So one way of adding functionality to the system is just to set more up and register them. And as more files come in, they're going to pick it up. And this is very important to understand, because one of the things that we want to do is we want to make it as easy as possible to write these extractors. And so this way, and I'll talk about some of the technical stuff later on, that separation is very, they're much more independent, so it makes it easier to write these components. Okay. So there's two building blocks that we're currently using for the DTS, which is prior work. One is Medici, the other one is Versus. I'll start with Medici. So Medici is a data management system for research data. The idea here is that you give it files, any file type, and the system accepts any file type, and then depending on these extractors running in the backend, it tries to do things with that file, right? So it's kind of like a Dropbox, but with these kind of extractors, little brown dogs running in the background, right? And so you upload first, you organize later. There's an aspect of Medici that is that of social curation. So we really talk about, in Medici, it's a management system where you just put things up there, and then the community kind of organizes those raw files. And so there's that aspect of social curation and also extensibility. So I've mentioned the extractors that run in the background. There's also another point of extension, which is the front end. And I'll talk a little bit more about them. But basically, instead of just showing a link to the file inside the web browser, we see if we can create a representation of that file that you can potentially interact with inside the web browser. This is especially important if you have very large files, right, gigabytes, and you don't want to download the full file before taking a look at them. So Medici itself is an open source project. And one thing that is never clear, is always hard to explain, is that it's a service where we host instances here at NCSA. So for example, we have 18 instances for the Seed DataNet project, 15 other random instances for use both internal and external. Brown Dog will be setting up this demo service that people can use. But really, the idea is that you can take these technology pieces and install them on your own resources. The code is set up in a way that we want people to do that, right? So it's not one service here at NCSA. It's also software that you can take and do whatever you please with it. We started Medici in November 2009. That's when we started the development of version 1. We had a public release in 2010 to give you a sense of kind of timeline. And we've been working on and off of it for several years now. In 2012 is where we started working on version 2. And a lot of the things that you see in the DTS, or a lot of the things that we have shown today and discussed, is primarily version 2 work. But there is this version 1 if you're interested. So when we started with several drivers, and one of the main ones was this idea that we get all these smaller grants, larger grants, but also smaller grants. We work with different communities, and it's always hard to adapt, and have a data management system that works well with the different communities. So one of the first things we said was, well, let's try to build a system that is extensible to different communities so that we can apply to physical sciences, biology, medicine, humanities, arts and social sciences, and so on. So what that means is that it needs to be able to handle all these file types, like Kenton was saying, right? Not one specific file type. And we all know why, there's all this data coming in and needs for why we want to organize this data, store it. And so the technical decisions were driven by these kind of challenges that we were facing. This is a list of funding sources so far for Medici, and we have this here because we want to emphasize that, as you can see, there's different funding sources, right? There is, it started the version 1 with Office of Naval Research, but since then there have been NSF projects, NIH projects, Exceed projects, European Commission, some private sector, EPA, now Brown Dog, and so in a way, this is in itself a mutt kind of, a software, project, right? And a lot of you guys are here in the room, so thank you for all your support. So this is a laundry list. I'm going to quickly jump to the next slides so that we don't all fall asleep reading that. This is a dataset page in Medici. So when a file goes up there for indexing or for extraction, there is also a UI component to it that you can go to and do the social curation. So what's usually is in these data pages is the data previewer, so ways of looking at the data, data provenance, so who uploaded it, the file type. There is licensing support, kind of things like the social tagging, informations about who you viewed the specific file, who downloaded it, if you have certain permissions, what collections this is in. There is then two types of metadata that is added by the user and metadata that is extracted by the system. The extractor is running in the backend, right? This is a dataset page. Here's an example of a previewer. So here we uploaded a zip file. Inside of that, one of the extractors was able to tell that there was a shapefile in it. So what it did is it took the shapefile, it registered it with the GeoServer, then it added to the metadata a URL for the GeoServer endpoint. And then when this page loads, the system kind of looks in the back and says, oh, you actually have a layer registered with the GeoServer. Let me put it on the page inside the map, right? And so you can interact with that map like you would, right, with a Google map. But it's important to keep in mind that kind of cycle, right? And that cycle is customizable. That's really the strength of the system. And that cycle is what Brown Dog is leveraging for the extraction stuff. Here's an example of a X3D PLY file. You can interact with it in the browser, change the lighting and all of that. You can play movies. This is an extraction service that looks inside the image if it finds GPS information. On the left, that's technical metadata. So that's a bunch of metadata fields that the user can look at in the page, but it's hard to read. But what happens is then the front end, looks and says, oh, you have GPS information. I'll show you a map on the right. This kind of use of the metadata that is extracted by the extractors, for further discovery. We also have ways of embedding files in external sites. Collection views. We have ways to select data sets, multiple data sets, and apply batch operations on them. A lot of these are well, I'll get to it. Never mind. Okay. Then we also have the ability of creating relationship between data sets, and a lot of this was used for provenance reasons. So we had at one point a desktop client that you could run analysis in it, and it would make these links for you automatically. And then in the web client, you can follow the trail. So in version 1, we did a lot with RDF. So everything was stored in RDF, native RDF. And if you're not familiar with RDF, is a semantic web technology. And so if you think about like a relational database, right, you have all these tables, you have all these, at the top fields. And, many times they're difficult to extract information out and make it portable. So RDF tries to help with that. It also gives you ways to do some reasoning on it. So the way it tries to do that is that it enforces all these URIs. So you have to fully qualify most of the information. And everything is a statement of subject, predicate, object. So this is how everything was stored. So all that metadata that the extractor would extract, it would all end up in this native form. And so we had this huge graph on the back end, and it was really, really cool. But it was also really slow at times because some of these systems are not as mature as database management systems that have been built for much longer, and that's okay. So I'll mention it in version 2, where we're taking more of a hybrid approach to this. So if you think about Brown Dog and DTS, all that this is all that metadata that gets extracted by the extractor. This is how it gets stored. There's a Sparkle endpoint in version 1. That's kind of technical. There's text-based search. So if you upload the PDF, it looks inside the PDF, extracts the text, puts it in an index. If there is image, there's metadata, it adds that to this text-based kind of search. And this is also important for the DTS because, like we said, once we start pulling in all these files, then there's always the question of how to find the information that you need. So we have to keep track of all these indices. Text-based search is just one type. I'll be discussing content-based search in a little bit. The Seed DataNet project is a current partnership, and as part of this project, the reason why I added these slides today is that I wanted to talk. So the Medici and this extraction bus is used primarily in the front. So there's 3 major services in there. The active content repository is the Medici kind of side of things. And the reason why I wanted to mention this and show this slide is that the virtual archive here is one of the links that we have to publish files that are inside the active content repository to long-term preservation, libraries, get a DOI back. So that's being done as part of this SEED project. We're also currently working on supporting ORCID IDs, not just in terms of adding as author of a file, but also as logging in using your ORCID credentials. That's work in progress, currently happening as part of SEED. I mentioned there's 2 versions. The 2.0 is the Brown Dog approved. That's because that's what Brown Dog runs on, right? So that's the code that we, shown today, the demo that we showed today. That's what it's running on. I'm gonna, let's see, 252. I'm gonna quickly skip through some of these because they're very specific to Medici, but they're, yeah. So in 2, let me jump to 2 because that's what we're really interested in here. The priorities for 2 have been 2 is in progress. We're building it as part of several projects. Is that to be scalable, maintainable, and extensible? We did some things in the first one to make that happen, but we're trying to, based on lessons learned, to really emphasize this. And so that extraction bus that I touched upon at the beginning, it was architected differently from what it was in version 1 to make it much more extensible and maintainable. So there's a lot of really good things there, useful things. And we also are modernizing the user interface because that's from 2009, which it's not that long ago, but time flies and there's different expectations. So this is too detailed. I'm going to jump that. This is the improved UI, just sample screenshots. You can style the UI if you want in different ways. One of the major things that we did was we made the assumption in version 1 to have a data set mean 1 file. And then we were like, okay, that's kind of silly. And it always, kind of came and made our life very difficult. So, we took the shortcut of uploading zip files, but really that's not enough because you really want to look at individual files in it. So in version 2, we have support for, multiple files in one data sets and all of that. Same flexible metadata. I'll touch upon this in a little bit. Okay, so that's Medici. So that's our kind of extraction bus for the DTS, plus all the data management that is required to keep track of the metadata, right, once it's extracted, because you have to put it somewhere, right? And so that's where this Medici fits in. Then Versus is a different building block that we have adopted, where the focus of Versus is to focus on customizable content-based file comparison. And what that means is that most of the time, if you're searching files and you're trying to compare files, it's easy to do it on the metadata that comes with the file. But if you have images, videos, there's a lot of information encoded right inside that file. And so Versus focuses on looking inside, that's content-based, right? And looking at the pixels and looking at the video and trying to make sense of that. And so, so we started building this for Nara. I have a slide later on. Several years ago. It's primarily Java code. It's a service. You can talk to it using REST. We have some clients. I think I should jump ahead because I have more of this on the next slides. So Okay, so sorry. Okay, so why content-based comparison? So you want to compare digital data, and given two or more digital objects, you want to establish the proximity. That's the simple case, right? So you have two of them, you want to establish proximity between the two of them. It sounds fairly arbitrary, but actually there's a lot of applications. So for example, Kenton mentioned the information loss in Polyglot, right? As you translate a file from one file format to the next, to the next, to the next, then you have to be able to ask yourself how much information was lost. And the only way is to compare, right, each version. And, well, you have to look inside and make sense of what's inside, right? That's really the only way. So that's one application. And that was the original driver for this particular tool. Content-based retrieval, so given a multimedia file image, find the closest one in a large collection, find duplicates across formats, right? So, how do I know that this version of this paper in PDF is the same as this other version of the same paper in Word? Here's an example of information retrieval problem. I'll talk more about it next, but the idea here is, these are cells from census forms from the 1930s, and we want to be able to specify a query, for example, Illinois, and then in the entire collection retrieve all the forms that have Illinois in it or a specific name, right? So that's an example of information retrieval as a problem. So this was primarily funded by NARA. Development started in 2010, originally focused on pairwise comparison. Over the past couple of years, we have added support for the creation of indices, so optimized indices, because for content-based retrieval, what we're doing initially was pairwise. In some cases, you have to do that, but basically the idea that you have to compare your query with all the elements inside your collection. Sometimes that gets really slow. You have to build these special indices to be able to do that, right? And so there's support for that in the service. Don't worry about the version. So two main components, a core set of Java interfaces, multi-threaded execution engines. Some of this stuff is a little technical, but basically the idea is you can embed this in Java code and build other tools on top of it, or you can write it, you can write your tools against the web service. We're doing a little bit of both in Brown Dog. There's several clients that we've built over the years, just to give you an examples, but all of them really either just talk to the RESTful interface or embed this Java engine inside the client. And again, I'll talk about some examples in a little bit, which will make it a little more relevant. So why use verses instead of specific implementations, which, it goes back to reusability. The big question, right, is well, I can just, write my own, method, and that's it. And in this particular case, for us, initially, it was one of these things where, okay, we were writing all these methods for these different projects, and it was really hard to apply them and to share them. And so I think everybody in this room understands the challenge here. So that's primarily why we build verses. And so the moment you kind of set up, a framework like this, then hopefully they will come, hopefully they will contribute. But there's definitely value for yourself independently of how big your community, how big of a community you can attract. So for example, so there's two major setups, and without looking at the code, and what we do is we take the task of content-based comparison and we split it up in these components, which some of you, if you're familiar with machine learning and AI, probably have seen these kind of things. But basically the idea is that these are our reusable blocks, right? So you get digital objects, and then you have some adapters. Those adapters can look inside the files. So similar to what, right? Because like what the problem that DAP tries to solve is, I might write a piece of code, but I don't know how to read a Word file. An adapter allows you to look inside the Word file. An extractor is what creates this feature representation. This is where there's potential information loss. Most of the time there is information loss, which is a representation, some numbers that represent, okay, the bytes in the original file, right? Okay, so that's your feature representation. Then in the case of the pairwise comparison, we have these measures, which given two features of the same type, it's able to give you a proximity value back, right? And so this framework allows you to have building blocks, so you can implement many different versions of these building blocks, and eventually you throw it two files and get a number back, right? So that's what Versus is trying to simplify. The index API works similarly, and it reuses some of the pieces shown in the pairwise case. So there's adapters, there's extractors, but instead it adds two pieces, an indexing piece and a query piece. And then you have this index. So it's mostly a formalization of something that almost everybody does, but it's very helpful if you're trying to pull in all these tools built by all these different people, right? You need something like that to make your life easier. There's a master-slave discussion, so we can run nodes on a cluster so that if we have specific methods that only work with specific architectures, we can do that. These are just lists. I'm going to just skip through them, but basically these are some of the methods that we have available currently in the framework. A lot of them deal with image data. I just want to show it because to emphasize the idea here is to get some momentum and build and put as many tools in as possible. So now we're going to switch to two, maybe three, depending on how we're doing on time. Maybe two, OK. So two examples, two use cases that have used these two technologies. One is the census, the use case that I briefly mentioned earlier on, that was primarily funded by NARA and Exceed. And the other one is the large-scale video analytics. So in this particular case, what we had was we got all these digitized forms for the census 1930 and then 1940. So we had the entire data set, lots of forms. They look like this, which, as you can tell, they're really hard to make sense of, right? And so what we wanted to do, we wanted to build a system that would make it easier to explore this data set, basically. Here's a bunch of them. And one way in which we prototyped the system in terms of exploration was you could go to the web or on your iPad, and you can either type a query like Illinois, or on the iPad you can actually try to write it in a similar way, and then the system does the query against the large collection. So that's kind of the goal that we had in mind. So the way the approach we took was, so this is a computer vision problem, meaning you have pixels inside the image, right? And so pixels are numbers, and there's a lot of them because these are pretty high resolution files. So the first step is that of going with through form segmentation. So you go through, because we don't want to be able to find the forms, right? We want actually to go into it and look at the specific cells. Ideally, that's the dream, right? So the first step is form segmentation. Now you have cells. And the cells look kind of like this. And they're messy, and you have to readjust them, right? So this is all computer vision. And then one of the things that we explored was, instead of try to use OCR methods, because it's really hard to map that to actual, right? Because they were written 80 years ago and by so many people across the United States, so many penmanship and all that. So what we do is we use other methods like word spotting, which tries to figure out the top in each column, the top, the bottom, where the black pixels are, how many black pixels there are, and what it spits out is 30 numbers. And so that's our feature descriptor, right? So in the previous slides. So now all we have to store is these 30 numbers, right? And so we do that in an index. And then when we go and try to search, what we started with was a linear search in a small set, and it was very, very slow. So then we started working on clustering, right, of all these 30 long arrays. And so we use different type of clustering. So if to speed up the search, right? And so this is an image that kind of shows the entire flow. And the reason why this is important is, let's see, do I have a slide there? But basically, it shows form segmentation, signature extraction, indexing. And the way this maps to DTS and brown dog is that we can these are things that we're formalizing in the DTS. So we're taking things like, given an original file, then output all the cells and relate all the cells with that original file, right, as a formal part of the DTS framework, so that every time we need to do that for new file types, we have that built into the framework. We just have to worry about the specific implementations of the algorithms. I'm going to skip this. This is another project with Exceed large-scale video analytics. This is a different data type. This is videos. So this is kind of the goals of the project. It runs on HPC resources. Well, we're setting it up on HPC resources at SDSC. And the goal here is to try to, one of the many goals, is to try to identify shots in videos and allow you to kind of jump between videos, right, and find similar videos as you're watching one. So what this is really, one of the big challenges is multimedia retrieval. These are, for example, shots identified for a particular video. You can see the time coding down below, start time 048, 159. And then if you go in here and you click on similar, similar goes back to the index, right? And our index, well, in this particular case, we're still doing linear search. So what similar does is it takes that shot and then it creates that feature descriptor, it goes to the backend, and then it compares that to all the shots identified in the system, trying to find similar ones. And so this was from a while back, but you can see that these two shots here, so that's your query on the left. And the shot at the bottom is, I think, is from the same video. The one at the top, I think, is a different video. It might be the same video, but you can see that there are two different shots, two different people. But because of the way the people are, in the shot, it's kind of matching them, putting them at the top in our search results. Here's another example. And the thing here is that we applied a bunch of different methods, and that's where the pluggability of things like Versus and Medici was very important, is that instead of knowing what the perfect comparison method and feature extraction method was, we just made a bunch of them, and we created all the feature descriptors, we did all the queries, and so here's a list of the ones that we are now porting to Versus to make available also to Brown Dog, to give you, again, to emphasize this idea that it's not just what these services can currently do, is really we are trying to build services that can be extended, more methods added, and so on. I'm going to skip this one. This is about GIS data. It's just this idea that, 307, let me skip this. Let me just touch upon this. So what happens here is that, actually this slide is a little more interesting. So what happens here is you upload files to Medici or the DTS. Some extractor runs in the background. These are CSV files. They're files from data loggers, from sensors on a boat. So they go out there, right? Sorry if I skip back and forth, but these are the sensors at the top. So let me do it. Okay. These are the sensors at the top. They're in the Great Lakes. They go in different points. They put the sensor down the water column. They get a bunch of numbers back. And now you have this particular CSV spreadsheet with a bunch of numbers in it. What we're doing as part of this project, we're aggregating a lot of data from different sources. So for example, we pull data from USGS, from their web services. And we need a way to put it all together to make it easier than to search and retrieve, right? Going back to the ability of making sense of this data, extracting information from the raw files. Right now, you will look at, usually what's done here is, people will send around these CSV files and that's it, right? What we're trying to do is build a system that can give you this and have a link back to the raw files. Well, how are we doing that? Is again, using this DTS service to try to extract this information out of the files, the raw files, and put them in a different form that is easier to make sense of that metadata. So here are the files that come into Medici. There's an extractor running. And then on the front end, you have different ways of interacting with that API, similar to the bookmarklet. OK, so some more technical stuff, a little more in-depth technical stuff. I'm not going to spend too much time on it. But one of the major aspects of the DTS is this extraction bus. Like I said at the beginning, you give it files, and then something happens. So for the more technical inclined, this is kind of what's happening. There's load balancers at the front end. There's a bunch of these services running in the cloud, and then one of them picks up a file. It stores it locally. This version of it is a cache, potentially. We're discussing how long it should be around, when it should be around. Then asynchronously on a job queue, you get this job saying, well, I got this file. I have some attributes about these files, so somebody do something with it. And then extractors that can do something with that information, with that file type, pick it up. They do something with it, and eventually they write back to the API. And the nice thing about this is that we're actually not writing directly to the database. We're writing to the API. So everything that you see in terms of the metadata, every way in which an extractor can kind of put information in and out, the client can also do. So as a client of Brown Dog, you have access to the same level in terms of the expressiveness of the API. And then the serial logs, which is primarily in operations issues. Once you have hundreds, thousands, or more of these running, then you gotta have a simple way of keeping track of them. So the way we do extractor registrations, and this is very important if you want to contribute tools, right? And you want to work on contributing tools to Brown Dog, to the DTS, is that the extractors are independent pieces of code that listen on some metadata about the file. Right now, it's the media type. So, for example, application PDF. They can do that. They can listen on a portion of that. So they can say, I want to just listen on images /star, right? So all kind of image files, and then on an object type. And that object type, the easy case is you throw it a file, right, and it works on the file. But we also have extractors that can work on collections, file sections, previews. So we have this data model in the backend, which if you work with the API, you'll come to learn. And the important things here is that we have the idea of a collections of data sets of files of sections, files as metadata. You can have metadata on data sets and so on. And the reason why this is important to keep in mind is that you can actually type extractors to specific things like that. So it makes it easier to have extractors that run on things like collections or an individual cell, right, in the census case, or a shot in the video case, right? It's not just the original file. You want to type the extractors to components of the file or collections of files, right? So that's how we can handle the different use cases. This is just a simple slide about privacy, and the only thing I wanted to mention is that right now the bookmarklet works in this context at the top. You have a public URL, it's public already, you send it to the DTS, we might cache it, then delete it, done, no harm done. We might keep it, we haven't really figured it out how we want to do that. But if you have something on your desktop, then you can take that file, you can go to authentication, create an account with the DTS, all of that, and that will go into your own space. So you can actually, if you wanted, use that for your with files and information that are not public. I'm going to skip this. I guess the down at the right is that extraction part. That's web app front end. Let me just skip this. We're running out of time. One last thing is that the way we're building a lot of these services is with this idea of being able to write different implementations behind the service. And this helps people that already have existing infrastructure that they want to reuse. So for example, we have a file service so that when you give it a file, right now, for us, it will either put it on the file system or it will put it, we have this MongoDB database implementation, we'll put it in that kind of database. Well, right now we're writing an iRods implementation, right? So we can reuse iRods. But from a user perspective, it's just the service, right? So this is more of a technical concern. But it's very important because this is what lets the system be adaptable to different use cases outside of our specific deployment. This is a bunch of technology for the geeks in this room. If you have any comments or questions about them, you can ask. But the reason why I put this here, besides the geeks, is that we're building a lot of these services on very well-proven technologies out there that are known to work well at internet scale. And we're doing that because, like Kenton said this morning, right, we want to make this a DNS type service, right? So we need to be able to give it all, throw at it as much as we can. I think I was supposed to go until 3:15, correct?
Yep.
Okay, so I was going to show you a bunch of information about what it takes to create extractors and versus metrics. I'll leave it. I won't spend too much time on it. You'll have the slides. But basically, in the case of extractors for the DTS, all you have to do is be able to talk HTTP and JSON, which most languages know how to do that. You learn the API, because that's what you need to talk to. And then you got to be able to talk. We're currently using RabbitMQ to do the messaging so that it scales well. So you need to, but the nice thing about RabbitMQ is that besides being well proven is that it has client libraries for most languages. And the payload of our messages is just JSON. So really, as long as you know HTTP and JSON, you should be able to write your extractors. I was going to show you the tutorial show you how simple an example in Python, but you can look it up. It's not that many lines of code. I was going to do the same thing with Versus. Versus is a little bit different beast because it's Java, so you have to kind of follow the Java ways. We use Java services, so I'll skip that. I was going to show you some, what the Java kind of interfaces look like to show you that they're not that complicated. But I'll skip that as well, given time. More information about these tools and the awesome people who contributed to this particular part of the project, contributed so far. If you're not on the list, come and kick me, and I will take questions.
So, Luigi, for every object type, you must have variety of characteristics that come out. So you have different facets or whatever to search on. How do you balance those, or can you tune those for different comparisons?
Yeah. So what we do right now is we are registering indices for different file types, and we're taking the easy approach of just searching every index and returning results from each one of them. We have some discussion going on in how to aggregate and normalize these, but the most difficult thing is that a lot of the metrics will have very different output. So the number that represents the proximity has very different characteristics in terms of statistic ranges. So normalizing that becomes a big challenge. And so, so from that point of view, we really haven't solved that problem. So we just say, okay, this index gives you these results, this index gives you these results, and then hopefully you know how to do it, how to deal with them. Well, if you have any other questions, I'll be around, so please.